I'm Paul Alivisatos. I'd like to take a moment before the science begins this evening for a special remembrance. It's very important for our community to take a moment and recognize a very, very special friend of science, Fred Kavli, who passed away earlier this year. Fred was a very special person. He was born in Norway, very entrepreneurial. Even at the age of 14, he had a company with his brother. He studied engineering in Trondheim, and after the World War, he sought to come to the United States for some adventure and to seek his future. He didn't make it on the first try. It was difficult for him to get into the United States, actually, so he spent a year in Canada. And then on the second try, he was successful. He settled in the Los Angeles area, and he worked in as an engineer in the aerospace industry. And he had a very successful run in that industry, and after a little while he decided to branch off on his own, and he started a company that made sensors for the aerospace industry and also for automotive and other industries called Kavlico. It's a very successful company, and after some years he sold the company. Those of you who had the fortune to meet Fred will know that he was a very engaging person, and he felt like he could just look right through you and understand you right away. But he also had tremendous business acumen, and actually he multiplied his fortune very substantially after he left the kind of engineering and technology world by being a very shrewd investor in real estate. Fred decided at a certain point in his life to give back to the world, and he did that in a very special way by his great devotion to science. And what strikes me as being particularly important, and what I certainly cherish in his memory, is that Fred specifically really believed in the beauty of science, and he had a fascination and a curiosity with the world around him. And so when he established the Kavli Foundation, he really dedicated it to fundamental science. As you heard from his biography, he was really himself an engineer. He built technologies that had widespread use, but he always held in his heart a deep devotion to science, and he ultimately chose 3 frontier fields of science in which to establish Kavli Institutes around the world, in astrophysics, in nanoscience, and in neuroscience. And he also supported a lot of activities in theoretical physics and mathematics. And he always held this piece close to his heart, that when he supported things, he really wanted it to be people thinking about the deepest questions in their field, the hardest problems, the things that we truly didn't understand. And that was a key part of him as a person, very curious and very driven person. We have an opportunity now to see a short video where we can hear about Fred in his own words. So if we could please have the video. Thank you.
I founded the Kavli Foundation in December of 2000 with a mission to advance science for the benefit of humanity and to promote increased public understanding and support for scientists and their work. I first came to Canada in 1955, and I started my business in 1958, just two years after I I came to this country, and 3 years after I came out of school. And of course, that's something I couldn't possibly have done in any other country. And started a business in 1958. Well, I wanted to do something that is of long-range benefit to mankind, to humankind. And I chose these fields because I think they're very, very exciting. And they offer tremendous potential just both in the near future and far into the future. I think that the study of the brain, the study of the universe, and the study of nanoscience can be of great benefit, and to some degree can be connected also. And that these different fields can benefit from each other. Science is taking us on an ever-accelerating journey into the future, which we cannot predict any more than we could foresee the revolutionary power of the transistor. Practically everything we touch in our daily lives has been developed and improved through basic research. And based upon the past, the benefits of science will be even more spectacular than we can ever imagine.
Good evening. I'm Tia Benson-Toll, this year's 2014 MRS President, and I'm sure I speak for all of us when I applaud and appreciate the foresight and the generosity of Fred Kavli. And now I'm pleased to introduce this meeting's recipient of the Fred Kavli Distinguished Lectureship in Nanoscience, Professor Yury Gogotsi of Drexel University. Yury's talk is entitled Not Just Graphene, The Wonderful World of Carbon and Related Nanomaterials. Yury?
Thank you for this introduction. I'm humbled and honored to be here. I feel also a personal connection to Fred Kavli because I spent some time in Norway at the University of Oslo as a postdoctoral researcher more than 20 years ago here. And today I'm going to spend about 40 minutes talking about material science, talking about nanomaterials and nanoscale science here. And you can see the title of my talk. But before I move forward, I also wanted to thank organizers of the Diamond Symposium and Energy Storage Symposia for nominating me to give this presentation here. So what I'm going to do today, I will divide my talk into 3 parts. I will be talking about carbon nanomaterials in general to give you a big picture of this exciting world of carbon nanostructures. Then I will show you on the example of supercapacitor electrodes, how selecting different structures, designing structures from carbon, and matching them to electrolyte allows us to achieve properties that we need. And at the very end of my talk, I will talk about a new family of materials most of you have probably never heard about, two-dimensional carbides. So going again towards a planar graphite structure. And About 2 years ago, I wrote this comment for materials today called "Not Just Graphene." And the reason for this was that we scientists like new toys. There is new material, we get excited, we work on it. There was first fullerenes and carbon nanotubes, now everyone works on graphene here. However, what is exciting about the carbon world is that it's so rich, there are so many different materials here. And I'm really not against graphene at all. I'm one of the organizers of Graphene Symposium, so you want to learn more about graphene, please come to our symposium on de novo graphene here. But today, there will be talk about the variety of carbons here. And really, I will try to keep it very simple. The slide you see now, probably most of you know from high school chemistry books. But there is really something very special about carbon atoms, structure of carbon atoms, and its ability to form sp, sp2, sp3 bonded structures. This is exactly the origin of the diversity of nanostructures that carbon can form. This is the reason why we all are built of carbon-based compounds here. So really, carbon is unique in this sense here. We can build a carbon world if you know how to do it, how to design this carbon, and I will show you just a few examples here. But exactly this variety, exactly this richness of carbon nanoworld makes it also very difficult for scientists and engineers to select the right one. Which one do you want to have for your application here? We can have sp bonded carbon materials, carbines, and we still don't know how to produce them. We can sit them in outer space as short 10, 11 atoms chains. We can make them inside a carbon nanotube, but not in bulk quantities here. Diamond is exciting. Nanodiamonds have many applications. We have a separate symposium on nanodiamond at this conference here. But today I will primarily talk about sp2 bonded carbon. Because of the case study I have chosen, because of conductivity that pi bonding in sp2 carbon like graphene, like carbon nanotube offers to us. But even if you look just at sp2 carbon, look how many of them exist. Graphene, nanotubes, fullerenes, onion-like carbon, which is a multi-shell fullerenes, nanohorn, nanocones. You can continue this list. And the most common material we really use everywhere are graphite, activated carbon, activated charcoal. Those materials are abundant, they're available, they really make our computer batteries, phone batteries work here. So, what do we really need for specific application? How do we select, how do we design with these carbon materials here? And really you can consider graphene to be like a basic element, basic structure. You can pile it up and make graphite crystals. You can introduce pentagonal defects and produce fullerenes, closed carbon shells, or you can roll them in seamless cylinders making carbon nanotubes. But even in this every family here, there is again enormous richness of structures. You can form a large variety of spherical shells starting from C20 and going to much larger numbers. You can also look at carbon nanotubes. There are single wall tubes with 1 nanometer and smaller diameters, but even those can be metallic semiconducting, armchair, zigzag, chiral. You can have double wall, triple wall nanotubes, multi-walls. They go larger diameters, they can contain catalyst or not. They can be cylindrical or polygonal. They can be conical. And then you can also smoothly transition to carbon nanofibers with these things here. You cannot draw really border. So it's a huge family of material along just carbon nanotubes here. And they are produced commercially and they are used here. And we can go on and on. You can produce carbon rings from nanotubes. You can also have conical structure. For example, Sumi Ejima, who is credited for attracting our attention to nanotubes, also produced nanohorns. And there are nanocones and microscopic cones, and they have different also structures produced by either introducing pentagons in the tip or by disclinations. You can see hopefully one on the screen here, even it's maybe a little bit too dark to see it very clearly here. And I already mentioned there are diamond particles. So sp3 carbon can also come in very small dimensions, about 5 nanometer, but they can be produced in a very simple way by putting explosive in the closed chamber, detonating it. What you do, you scrape diamonds off the wall of this chamber here. I'm not going really to talk about diamond today in this presentation, but what is important, this material can be produced in larger quantities at moderate price, and by annealing it, we can transform diamond crystals to multi-shell fullerenes, which are called carbon onions. And then I will talk about application of those in electrical energy storage here. And you can go on and on with a variety of nanostructures. But again, as I mentioned, what is really widely used are conventional carbon material. This is what is produced in ton quantities every day. We have activated carbon in Brita filters that we use for filtering water. And of course, those materials are nice because they're first of all inexpensive and also come variety of structures here. However, when you take a natural precursor, it's very difficult to control, for example, porosity of activated carbon. You cannot control number of sunny days on a Pacific island where coconuts grow. However, we can start with metal carbides, with crystalline structures where we exactly know how many carbon atoms will be per unit of volume of this material. And extracting metals produce again carbon by, for example, these reactions, but we will be able to control the structure, density of carbon, distances between the carbon atoms by taking a specific structure. For example, silicon carbide, we have a diamond cubic lattice, or max phases, so known ternary metal carbides with layer structure. As a result, we will get either very narrow pore size distribution with 8 angstrom pores, or much broader or multimodal distribution. Of course, carbon will not necessarily stay in an ordered structure after extracting metal atoms. Usually we'll get this type of amorphous networks, and they are extremely amorphous even at the highest temperature. However, you will not be able to find any fringes at lower temperatures, and there will be more ordering in three-dimensional network occurring at high temperatures. So we learn how to make structures. We make, for example, carbide-derived carbon by electrochemical etching even at room temperature. And we can, in general, even by extracting metal carbide, but this simple single technique, produce almost everything from porous carbon networks to graphite, nanotubes, and graphene. This is exactly how many of us make graphene layers on silicon carbide crystals, by removing silicon atoms from the surface of silicon carbide. So we have a variety of methods to make carbon materials here, and we can produce what we want here. So what I'm going to do now is to show you how we can use and why we need different carbons with different structures, with different properties. For example, for electrochemical energy storage, specifically supercapacitor electrodes here. And I understand that many of you here in this room may not necessarily be familiar with supercapacitors. Those are actually devices somewhat similar to batteries. They come in similar format, similar size, and we also use them to store electrical energy. But unlike in batteries, we have physical storage, adsorption of ions on typically porous, high surface area conducting electrodes with low losses, high rate, and they are similar to batteries. They have two current collectors, they have porous electrodes, and they're called supercapacitor because unlike electronic capacitors, which are usually rated for microfarad, millifarads, we can store farads or hundreds or even thousands of farads in the same device here, and there is electrolyte in between. So simple structure. And the idea of storage is also very simple. We adsorb ions on the surface of carbon with a high specific surface area here. This is how the device works here. So, if you look at charge storage in these devices, it's really the performance. Everything is determined by the carbon here. So what happens? We have carbon material which can have different structure. We can take nanotubes, we can take graphene, we can take carbon onions, multi-shell fullerene I showed you before, or we can have a porous network. We charge the electrode and oppositely charged ions will be attached to the surface. This mechanism is different to what is happening in batteries. As a result, electrical response will also be different. In a battery, where you discharge a battery in your computer or cell phone, the battery keeps the same voltage and the voltage drops at the end, like is shown in this galvanostatic plot. When you discharge or charge supercapacitor, there is a linear change of potential with current here. And cyclic voltammogram will also look different. There will be this rectangular one for supercapacitor, and you will see clearly pronounced separated peaks in case of batteries here. So these devices really complement each other. If you look at this plot, which we call Ragone plot, it shows dependence on specific power and specific energy. For example, if you talk about a car battery, specific energy shows you how far you can go on a single charge. Specific power shows you how well you can accelerate. And you will see that supercapacitors or electrochemical capacitors, they are also called double-layer capacitors or ultracapacitors, bridge to a certain extent the gap between solid state or electrolytic capacitors and batteries. They have higher power density, so they can be charge-discharge very well within second times. On the other hand, they have lower energy density than batteries. You see lithium primary batteries here, lithium-ion batteries here. So what they can provide us, they can provide us power, but also important to remember, within a short time, you will be able to store or harvest more energy as well, as long as you talk about processes that last less than a minute here. Also, what is important, we can make these devices all of carbon-based materials. So we can make them recyclable, and this is becoming specifically important when we have more and more electrical energy storage devices, and we will need to think about a problem of recycling those here. And they already find numerous applications here. For example, you can see in trams in Germany powered by supercapacitors, they use 30% less energy because they recover breaking energy and reuse it. The same is done in gantry cranes that can be recovering up to 40% of energy from diesel generators here. You can see this type of trolleybuses in Shanghai Street. Instead of developing a battery that will last for 8 hours, you have here on the top of this bus a supercapacitor battery set up here. It will just last for a few kilometers, but since you can charge and discharge it within 20 seconds, during the time people get on and off the bus, it can be fully charged here. So what is important? We need to think outside the box to develop with the new storage solutions like supercapacitor. And last example I want to give you here is this type of bus stops installed in Japan in remote areas. The roof is a solar battery. You have two LEDs here that provide illumination, and under this bench where people sit here, there is a battery of supercapacitor. You may ask logically why? Why not a lead acid or lithium-ion battery that would last longer and store longer time? The reason is very simple. The entire system is guaranteed maintenance-free for 10 years. You install it once and it will operate, no wiring required, no nothing, and will provide lighting here because supercapacitor have cycle life up to 1 million cycles, sometimes even longer here, because of this electrostatic energy storage here. So there are many applications. You can make also this supercapacitor wearable, embed them into smart textile, embed them into flexible devices, sensors, electronics, and many others. And this is what is exciting about those materials. And as I already mentioned here, what you really have in the heart of all these devices is carbon. So carbon is everywhere there, depending on how conductive it is, what is the surface area, supercapacitor will perform better or worse. Moreover, if you look at this model of capacitance versus particle or pore size, you will see that different carbon morphologies, if you assume the same conductivity, same other properties, will behave differently. For spherical particles, we will see increasing capacitance significantly with decreasing size of the sphere. Tubes will go here. Planar materials like parallel plate capacitor graphene will be laying in this area. Mesoporous carbon, carbon with pore size larger than 2 nanometer will show in a very different dependence, and microporous carbon will end up here. So again, we need to know how to select the material to achieve the optimum performance here. Moreover, if you design an electrical energy storage device, a supercapacitor, you have carbon electrode and you have electrolyte. Now, I hope I've convinced you that there are numerous carbon materials to select from, a huge family. But now again, you can use aqueous electrolyte and salt water, organic electrolytes that are used to increase the voltage window because energy stored is proportional voltage square and water will break at about 1.2 volt. And you can also go to ionic liquid. So the question arises, how to match this specific carbon to a specific electrolyte? You cannot do it by randomly selecting a good carbon and a good conductive electrolyte here. Moreover, if you use, for example, highly porous materials, use very thin coatings, you can also get results that will look good in the lab, but not really good when you move to practical application here. So what we did when we started to work in this area, and we developed carbide-derived carbon materials with controlled porosity, we just wanted to check what happens if we control the pore size in carbon network with a high accuracy, much higher than people can do it in conventional carbon materials here. And we produced a number of carbons. You see with the pore size is changing from less than 7 angstrom to about 11 angstroms, and with maximum pore sizes being actually smaller than salvated pore size here. And the question we ask here, what happens if pores are just too small to accommodate ions? We all know from chemistry courses that we took in school or colleges that ions are solvated in solution. And conventional wisdom was telling that ions go with salvation shell. They need to line up pores, as I showed you in schematics before, to give you storage, electrostatic energy storage in supercapacitor. And the results that we obtained was very surprising. We expected capacitance to drop close to zero at pore sizes approaching 1 nanometer because this pore size was smaller than the salvated ion size. But as a result, what we found that capacitance actually increased and increased dramatically with decreasing pore size. So a natural and very simple explanation was that ions go into pore without salvation shell, at least partially naked, losing some of the ions in salvation shell. As a result, we can pack more ions since this salvation shell is lost. The distance between the charges becomes smaller, capacitance becomes larger. And this seemingly simple result led to really a dramatic change in the entire development of capacitive energy storage devices, attracting the attention of researchers, moving scientists into this field, and understanding there is a lot of design can be done. Modeling very quickly showed that really this is exactly what is expected for small pore sizes in case we consider not mesoporous materials with ion salvation shell, but ions in micropores here. And there has been tremendous amount of modeling and simulation and atomistic modeling done over past few years to understand adsorption ions and form, confinement of ions at the surface and in porous materials here. An example I show you here actually is next steps that we did, trying to move from salvated electrolyte to ionic liquids. Ionic liquids, room temperature ionic liquids, are electrolytes which are basically organic salts liquid at room temperature here. There are no solvents there. They are non-flammable. They have very low vapor pressure, potentially would be wonderful electrolytes, but they are viscous. They require high temperature testing here. But for us, it was a very interesting model system because we wanted to see what happens when ions don't have a salvation shell. And what we found was very interesting. We found that again, the maximum incapacitance is observed at the pore size, virtually perfectly matching the ion size. However, I wanted to attract your attention to this scale. You see, change of the pore size by 1 angstrom leads to about 50% change in capacitance. When pores are too small, ions just simply cannot go into pores. When pores are too large, you still cannot fit more than 1 ion in, say, 1 nanometer pore if the ion size is 7 angstroms here. So naturally, you have a very narrow pore size distribution. that is required to achieve maximum capacity. So we go beyond even nanotechnology. We need to be able to control our materials with angstrom accuracy if we want to develop materials that show the maximum performance here. That's why this nanoscale is really important. And again, very similarly, modeling simulation by using molecular dynamics and DFT quickly confirmed, yes, there will be exactly this type of a peak at the pore size corresponding ion size. Moreover, there will be second and third peak oscillation of capacitance as 2 or 3 ions can go into pore here. But what you also would notice, if you look at a variety of papers published by scientists who did modeling simulation for this system, all of them were done either on cylindric pores, like carbon nanotubes, or slit pores, like in graphene or graphite here. However, I showed you before structure of real carbon, or you take activated carbons here. They don't have slit pores clearly shown here. They don't have cylindric pores. They're three-dimensional networks here. And working with Keith Gabin's group, we were able to produce models of carbide-derived and activated carbon. And Matthew Salan at University of Paris 7 did molecular dynamic simulation showing that actually ions will go into pores of this material. Moreover, in case of say ionic liquids, negative ions will drag positive ions along and vice versa. So there are always counter ions penetrating into these pores here. So basically what is happening, slowly, step by step, from a very empirical field where people were developing devices by using activated carbons and trying to match them to electrolytes here, we get more and more understanding what is really going on with ion confinement, how they behave, transport characteristics, performance, storage here. So we come to the stage when we can develop really materials that match our requirements for performance. And you will also see by using the same MD simulations that, for example, planar graphite and three-dimensional network, even close to graphitic structure, will have different characteristics. Ions will be at different distances located from the surface of the material. So really, different materials behave differently here. And at a certain point, we were very happy with our finding and our knowledge. We knew how to make the best supercapacitor material here. Everything is simple. We take plates of materials, 100, 200 microns thick, with no mesopores, no macroporosity, with just micropores tuned to the size of ions, and we will make the best electrical energy storage device ever. And of course, we produce these plates. We make carbide-derived carbon films ranging from microns to couple of hundred of microns by transforming, for example, titanium carbide into CDC. And we got actually wonderful performance, 100 farad per cubic centimeters, 3 times that of commercial supercapacitor. But as you see, just for 1 micron films. As the film thickness increases, capacitance decreases, going actually below state-of-the-art devices. And the reason you can understand in a very simple way. Consider you have a 100 micron thick film with 1 nanometer pores. An ion must jump through 100,000 pores to reach the current collector. Of course, we simply hit diffusion limitations. We cannot fill all the pores. We cannot store charge efficiently here. So, how can we solve a problem? How we can make a device that can be really quickly charged in all area used here? We can use different carbon materials. We can use, for example, multi-shell fullerenes, carbon onions, or nanotubes, which don't have internal porosity. Well, all the accessible surface area is on the surface of these particles here. And if you make a device using, for example, carbon onions, you can charge those devices with the rate going up to 100 volts per second. You see, up to 100 volts per second, we get linear dependence on discharge current on scan rate here. So imagine it takes you about an hour to charge your computer battery, or a couple of hours usually to charge a phone battery here. Here, if your device is a 3 volt, 2.7 volt, usually supercapacitors with organic electrolyte here, you can charge them in tens or hundreds of milliseconds here. So it shows how by changing the structure of carbon, we can go from seconds, tens of seconds charge for activated porous carbons to millisecond charges of the material here. And of course, in this case, we can already move on a plot, and actually this is a Ragone plot somewhat similar to the one I showed you before, comparing simply thin film lithium-ion batteries, supercapacitor, electrolytic capacitors here. What is interesting, you will see. By using carbon-onion micro-supercapacitor, we can have specific energy actually comparable to thin film batteries, but we get into specific power range of electrolytic capacitors, and those are among the largest and least reliable devices we have in our cell phone elsewhere. So we can increase the power, we can actually really get into different range of application, like AC-DC conversion, filtering, and electronic application here, simply by selecting a different material here. And you can do a number of other things here. I mentioned to you before that, for example, for ionic liquid electrolytes, people could only do experiments at elevated temperature and design devices with porous carbon that would work at temperatures above room temperature here. However, when we have learned and realized that by using open structures, we eliminate large diffusion limitations here. What we did, we took a mix of ionic liquids, eutectic mix, that doesn't freeze down to -80 degrees C. It may have lower conductivity, high viscosity. What our thinking was that if we don't have pores in which ions need to diffuse here, if we just have absorption of ions on the surface, we should be able to expand the temperature range here. And we tested this hypothesis using carbon nanotube electrodes here. What you see happens, we can charge a supercapacitor which is made of an aluminum foil with grown carbon nanotube at 100 degrees C and actually do it at extremely high rate, going up to 20 volts per second, which is really believable for ionic liquid electrolyte. But we still can charge it at -50 degrees C, keeping the same nice rectangular perfect capacitive performance here. So before this work, there was really no single paper showing that ionic liquid electrolyte can be used below room temperature at all. And here, simply by designing the carbon electrode, we can push it down to -50 degrees C. And you can do exactly the same thing on carbon onions or graphene electrodes here. So as a result, by playing with carbon, by designing with carbon, by understanding how to match carbon electrode materials and electrolyte, we will be able to expand the temperature range from -50 to 100 degrees C for electrical energy storage application. So if you have this as a battery in your car, you will be able to start your car in Alaskan winter or Arizona summer, and you will be able to operate it safely because ionic liquids are non-flammable and have very low vapor pressure here. However, activated carbons that people use nowadays have specific surface area about 1500 square meter per gram, while carbon nanotubes or onions have just a few hundred square meter per gram surface area, naturally giving a lower capacitance. However, here we also have graphene, for which theoretical specific surface area for a single sheet of graphene is 2600 square meter per gram. And Rod Rueff published a couple of years ago a paper deporting on activated graphene. They called AMIGO, activated microwave reduced graphene oxide here. So this is like graphene considered with drilled hole with high specific surface area, showing actually pretty good performance at room temperature in ionic liquid organic electrolyte. So what we did, working with Rod and his group, we produced supercapacitors using the same ionic liquid eutectic mix that I showed you before in application to carbon onions and nanotubes. But now what we obtained by using graphene, where again ions don't have to diffuse through a network of pores that jump into holes in layers of graphene, we were able to achieve about 170 farad per gram capacitance, which is at the level of the best organic electrolyte supercapacitors. But we were able to go up to 3.7 volt. Since, as you may remember from the equation I showed you, energy is proportional capacitor voltage square, it pretty much right away doubles the capacitors of the device. Moreover, we can still go to high temperatures and we can get a very good capacitance level of current devices at -50 degrees C. So again, by designing this carbon, we can improve performance, improve capacitance, and at the same time keep the temperature range here. So there are many, many different opportunities here. And I would like to conclude showing you that we can also go beyond pure carbon if we're looking for other properties that we cannot achieve in currently available carbon materials here, and talk about two-dimensional materials which are related to graphene here. And of course, graphene is the most typical, best known, most common example of two-dimensional materials here. However, metal oxides, hydroxides, including clays, are definitely the most widely used ones here. There is hexagonal boron nitride, which you consider to be basically structurally analogous to graphene, just with boron and nitrogen atoms. Here are metal dichalcogenides, for example, molybdisulfide and other things here. However, so far there have not been any transition metal carbides made in a two-dimensional state here, until we discovered about 3 years ago an entirely new family of two-dimensional materials based on metal carbides here. We call these materials MXenes because they're built of M and X atoms here. And what you see here is the cover of the journal. This is the first publication on MXene, which appeared in 2011. And this is the first actually review of the field which was published in Advanced Materials at the end of last year here. So the oldest one is just a 3-year-old baby. Younger ones, and we already produced 13 of these materials, is just a couple of months old here. So there are these 3 different lattice structures are possible with M2X, M3X2, and M4X3 formulas here. So how are they made? Why are they called MXene? We take MX phases, which are layered transition metal carbides, nitride, carbon, nitride, built of this M element. A element is one of this element from this group, and X stands for carbon or nitrogen here. This is a very well developed and studied family of ductile ceramic material. My colleague at Drexel, Professor Michel Barzoum, is really the father of this field. And there are many of these materials. Some produced commercially. More than 70 phases have been synthesized and studied here. And you can consider them very simply as a single, double, or triple layer of carbide separated by a monatomic layer of A element atoms here. So what we did was fairly straightforward. We etched away this monoatomic layer of metal, specifically aluminum from titanium aluminum carbide, by initially etching hydrofluoric acid. And if you do this etching, you will end up with this structure, which looks very much like exfoliated graphite, which is used in battery electrode and may look familiar to people who work on graphite here. And if you sonicate it, you can get single flakes of this material. And this material behave in all aspects just like other two-dimensional atomic crystals here. They are transparent in nanometers thin films. If you do atomic force microscopy, you will see that those are 1 nanometer flakes correspond to a single layer MXene structure, titanium 3C2. You can see in transmission electron microscopes that you can get single layers, those are separated far, multi-layer or double layer, triple layer MXene. They maintain their crystalline lattice ordering in the film here, as you can see also from high resolution TM electron diffraction. Like other thin layers, they can roll into scrolls just like a graphene, or it was also has been predicted theoretically that nanotubes, seamless nanotubes can exist. They have not been made yet, but they're possible here. And what is important, by now, within this less than 3 years, we were able to show that all 3 types of MX phases, 211, 312, or 413, can be transformed into MXene two-dimensional carbide here. So the representative, all 3 of them. We can obtain solid solution on M side. We can obtain solid solution on X side here. So it basically means that pretty much any MX phase can be transformed in two-dimensional carbide, carbonitride, where still to synthesize nitride, although they have been predicted by DFT calculation by a large number of groups to be stable as well, still somewhat less stable than carbides here. So we really have a totally new family of two-dimensional materials, and again, they can be produced in single flakes. You can filter colloidal solution, make MXene paper just like you make a graphene paper. And also, DFT calculation experimental measurements showed they have a metallic character of conductivity. Also, surface termination can open the band gap from less than 0.1 electron volt to 2 electron volt, depending on the composition of these materials here. So we can make again conducting, very strong and thin materials here. And what is also important, of course, you can intercalate ions between these layers just like you intercalate ions between graphene. But when we did capacitance measurement on those materials, we found that, unlike in graphite, that shows real electrochemical behavior and intercalation of lithium ions, for example, and better release to electrochemical reaction here, we get pretty rectangular cyclic voltammograms. We get ideal, virtually triangular galvanostatic charge-discharge curves. And we get extremely stable capacitance for 10,000 cycle, and you can continue these things here with very low resistance, and this Nyquist plot shows here. So basically, we have a new family of materials with high volumetric capacitance. This capacitance is really intercalation capacitance, because ions, as I showed in the previous slide, just go really between this layer, but without noticeable charge transfer here. We have excellent cyclability, and we have also good electrical conductivity. Moreover, I mentioned to you before, when I was talking about porous carbon film, that achieving 180 farad per cubic centimeter capacitance was pretty remarkable, because this is 3 times of what commercial devices show. You can see numbers now exceeding those numbers by about a factor of 2. And these are really very first experiments done on those material. As I mentioned, the oldest one is a 3-year-old baby here, and this work was done just last year here. So there is clearly tremendous new opportunity to study those new carbon-based materials, understand mechanism of this intercalation capacitance, and was recently also observed for some layered oxide like niobium oxide here, and develop much better materials for application here. To basically summarize and wrap up my lecture, I wanted just to mention here, there is no perfect material. Carbon is really extremely versatile, the most versatile of all materials. We can get any properties in carbon. The hardest materials known to one, diamonds, carbon. Soft, lubricious, graphite. We can get materials which are dielectric like diamond, wide band gap semiconductor, doped diamond, materials with tunable band gap like nanotubes or graphene ribbons, or materials with better conductivity than copper because of ballistic conductivity in graphene and nanotube here. So, if we know how to design this carbon, we can probably achieve virtually any combination of electrical, mechanical, optical properties in carbon material. We just need to know how to design, and potentially nanoscale science engineering allows us to do it. We can do it all, we just need to set the goal, we need to know what we want, and we can go and produce really exciting things building with carbon atoms. And if this is not enough, we can go beyond that and, for example, make carbides and other carbon-containing compounds and structures, as I showed you an example of MXenes here. And at that point, I'm going to wrap up. I just wanted to acknowledge many people who contribute to this research over the years here. We collaborate with a group of Patrice Simon in France on capacitive energy storage, with Michel Barzoum at Drexel. Much of this work was supported through first EFRC in the past few years, and there is a very large group of researchers at Oak Ridge National Lab and Argonne National Lab and elsewhere participating. I have excellent collaborators pretty much all around the world here. This is a list of former students and my current students, and pretty much all of them except Changren and Olha Mashtalir are here at this conference now. And of course, support from Department of Energy through EFRC, from Basic Energy Sciences, ERE, BATT program, and others appreciated. National Science Foundation, Division of Materials Research, and chemistry programs here. Partnership University Fund support our collaboration with France. Some initial funding came from DARPA here. And those are really people who did all the work that I showed to you. This is my research group, a picture taken just a couple of weeks ago at Drexel on a sunny day in Philadelphia. And many of them will be presenting papers here. I specifically wanted to attract attention to Michael Naguib's presentation on MXenes. Michael will be competing for Gold Graduate Student Award here, but there will be quite a few other interesting posters and papers presented by the students. And again, thank you very much for your attention and time spent in this room this evening. And I will be glad to answer a question if this opportunity is offered. Thank you very much.
Thank you so much for this very interesting lecture. We'd like to give you this memento honoring your Fred Kavli Lecture in Nanoscience here at the 2014 MRS. Thank you. So we do have time for a few questions. If you would, come right up to the microphones in the aisles.
Hi. Yeah, thanks for a great talk. I was just wondering about the cost of making your CDC type materials, and can you see an alternative to using HF in their production?
To MXenes materials?
Yeah, or any of the more complex carbon materials.
Yes, we actually do have alternatives to it. You can also HF containing salts, and we have developed a new method which unfortunately I cannot talk about right now because of the patenting and technology transfer negotiations, but yes. And you can basically use your imagination and knowledge of chemistry to guess that other chemistries are possible. Sorry, I cannot really expand on this right now. Hopefully in a month or two.
Oh no, it's just good to know it's being done. Thank you.
Yeah, so you have a safer way to etch it when no HF solution is involved.
Do we have any other questions?
Hi, I just want to say first, thank you for the lecture. And secondly, this presentation, all the MXenes stuff was very heavily focused on supercapacitor applications. But if it has intercalation capability, it could actually be used as a battery material. So I was wondering if you could expand maybe on any potential battery applications that you were looking on.
I'm not sure I understood the end of the question, but basically, again, the point was that I talk about supercapacitor but not about batteries. Well, basically, the challenge with such a presentation always is here, that you cannot cover everything. I had to select just an example. First, much of what I was talking about in the first part of my lecture can be related to other materials. For example, we develop porous carbon for supercapacitor to match pore size to the ion size or ensure adsorption on the surface. By the same token, we developed porous carbon networks for storage of hydrogen or methane or carbon dioxide gas molecules. But we can go from sub-nanometer sizes required for this application to 10 nanometer pores, which are required to remove proteins, cytokines from blood plasma for hemasorption of the materials here. So you basically can use it just as an example of the approach. Very similar way, For many applications, when we use carbon materials in supercapacitors, we can use them also to store, for example, lithium ions in batteries, or building, for example, lithium-ion capacitor, which are devices intermediate between battery and supercapacitor, like with one battery, one supercapacitor, like electrodes here. We studied MXenes for lithium-ion battery applications, and also something I did not stress, but we can adsorb magnesium, aluminum, so multivalent ions between MXene layers. And there are very few materials which actually allow you to get this larger and multiply charged ions into solid state structures. So we are very much also excited about exploring these materials for battery application. And this, I would say, would be a natural field for study.
Thank you.
Looks like we have one more question.
Thank you, Dr. Gogotsi. I enjoyed your talk today very much, as well as the talk I invited you to give at Texas A&M a few weeks ago. And my question today is that so far, only the carbide max phases has been made to MXenes, and no nitrides is being done. And what was the major reason for that?
Well, there may be a couple of reasons for this. We were able to make carbon nitride, and I will be talking a little bit more in my lecture on supercapacitor application tomorrow here. We did try to etch nitrides, but so far the selectivity was not good enough to produce nitride, pure nitride here. And there may be a reason for this. DFT calculation done by a Russian research group by Yanashin and Ivanovsky showed that while nitride are stable, their stability is somewhat lower compared to that of carbide. So we just may need to have a more gentle and approach to selectivity here. But to be honest, I don't think we have put enough effort, producing certain new materials in about 3 years. That's a lot of work if you try to characterize here. So I'm sure it should be possible. It just will probably require more effort and further efforts. Also, within this group of material, imagine you have a new family of material emerging within a couple of years. This is certainly not something that Michel Barzoum and myself can do, even with all the enthusiasm of our students and postdocs. This will require entire community to work on. There are many groups that already do modeling simulation of MXenes. There were several groups that published some exciting research results, but it will take materials research community to really explore those materials. There are thousands of people working on graphene alone here. Here we have so many new two-dimensional materials. It will take a lot of effort and some time before we can really understand what is possible, what is not, which of these phases can be produced, how they can be produced, and what properties they can offer to us.
All right, thank you, and congratulations.
Thank you. And with that, I think I'd like to just echo his call that it will take the materials community to continue some of this very exciting research. And let's thank Professor Gogotsi again. He and his students will obviously be sharing some more of the research throughout the week. Thank you.